So today we'll talk about the formulation of quantum statistics. Okay, so let me start. Uh, the ensemble theory. So far we have talked about the different ensembles, right? And then now we'll talk about the formulation of quantum statistics. Now, the ensemble theory developed earlier is extremely general, though the applications considered so far were confined to either classical or quantum systems composed of distinguishable entities, right? That is what we did so far. When it comes to quantum mechanical system composed of indistinguishable entities, as most physical systems are, that most physical systems that you deal with are mostly the particles. It's composed of particles which are indistinguishable, right? And the ensemble theory should be rewritten in the language of operators, wave functions. So you have to adopt the quantum, you have to take the help of quantum mechanics. So, rewriting the theory may not apparently seem to introduce any new physical ideas. However, it will suit the quantum mechanical system better. Okay. Furthermore, in asymptotic limits, means the classical results will be reflected. I mean, generally we do. So far, we have done in the special cases, right? In special cases, what we have done, we have looked at. Hey, Ramit, hello, Ramit.
হ্যাঁ হ্যাঁ স্যার।
এত দেরি করলে কেন?
স্যার এটা কানেকশন প্রবলেম হচ্ছিল স্যার, আমি অনেকক্ষণ ধরে চেষ্টা করছি।
ও আচ্ছা, এবার ঠিক আছে?
হ্যাঁ স্যার, হ্যাঁ।
Okay. So we also consider that the asymptotic limits are intact. Okay? So classical results will be reflected. For instance, at a high temperature and low densities, the system will behave classically, and hence in these limits, the results obtained with a new approach will reproduce the classical results. That is what you expect. When you adopt a new theory, definitely you look at the new theory and you try to figure out, or rather with a new theory you do calculate the quantities, and finally you see whether these quantities do agree with the classical results or not. That is what you always try to check when you adopt a new theory, or when you think of a new theory. Okay. আচ্ছা, মৌসুমী, সিনথা and others, তোমাদের এত দেরি হলো কেন?
স্যার এখন আমাদের স্পেশাল ক্লাস ছিল, ওটা এখনই শেষ
হ্যালো?
হলো। হ্যাঁ, এখনই ক্লাস শেষ হলো, তাই স্যার।
তো স্যারেদের বলো অন্য ক্লাসে যে ক্লাস ছেড়ে দিন, কারণ অন্য ক্লাসে ডিস্টার্ব হয়। এই একের পর এক তুমি দেখো যারা রয়েছে তারা বুঝতে পারছে আমি কি করছি, আমি যা শুরু করছি আই এম গোয়িং টু অ্যাকসেপ্ট পিপল। হ্যাঁ, অন্য স্যারদের বলো যে প্লিজ ডু মেনটেন দ্য টাইম। হ্যাঁ, অন্য ক্লাসে ডিস্টারবেন্স হচ্ছে। আর দেখো, আবার দেখো, বুঝছি আই কিপ অন ডুইং দিস। কোন কি ক্লাস ছিল তোমাদের?
স্যার স্পেশালের ক্লাস ছিল।
স্পেশালে কার ক্লাস ছিল?
স্বপনদার।
হ্যাঁ, তাহলে স্বপনদাকে বলো যে মেনটেন দ্য টাইম, কারণ এইভাবে ক্লাস হতে পারে না। আমি জাস্ট আই এম স্টার্টিং এন্ড পিপল আর এন্টারিং। আমি তবু 5 মিনিট পরে শুরু করেছি, জানি যে একটা ক্লাস থাকলে 5 মিনিট পরে আসে। আমি হোয়াট ইজ দিস? হ্যাঁ, তোমাদের কোনো দোষ নেই, আই এগ্রি উইথ দ্যাট, বাট পিপল শুড বি কাইন্ডস। এইরকম করে কি পড়ানো যায়? হ্যাঁ, এটা শুরু করছি, মানে কতবার হলো, 10 বার হলো, জানো তো এরকম। Anyway, so what I said, that when you adopt a new theory, basically you will take care of the quantum, this one also, quantum mechanics will adopt, and will adopt a new approach. When we adopt a new approach, we try to get the results, and eventually those results should be checked, such that in the classical limit, the results is reproduced. Okay, you see, তোমরা বুঝতে পারছো? আবার আবার see, দেখো এইভাবে কি এগোনো যায় বলো? দেখো, দেখো, তোমরাই বলো যে এইভাবে হয় বলো, আমি কি করব? পড়াতে গেলেও তো একটা মানুষের একটা আসে না, মানে একটা ফিলিং, একটা সিচুয়েশন। হ্যাঁ, anyway, the results obtained in the new approach will reproduce the classical results. In the process, we'll automatically obtain a criteria which tells us whether a given system may or may not be treated classically. Okay. So when you adopt new things, then definitely there will be a situation under which you say, this is the situation, at this situation you will get the classical results, or otherwise you won't get. Okay. So, but the bottom line is, when you adopt a new theory, you try to see the special cases and see whether do they agree with the earlier classical results or not, under such suitable circumstances. When we look at the quantum mechanical ensemble theory, the density matrix approach. Okay, and this is what we were given to write a project on, right? But still, it will be easier for me to go through because you have already probably gone through it. Now consider an ensemble of eta identical systems where eta is very, very greater than 1, right? These systems are characterized by a common Hamiltonian, which may be denoted by the operator H. Suppose that you have a system, an ensemble, and means in identical systems, and each system, of course, will be characterized by a common Hamiltonian, and which is denoted by H cap. Now, at time t, the physical states of various systems will be characterized by the wave function. You know that. You know quantum mechanics. You have gone through quantum mechanics in detail, and therefore you know that the physical state of various systems will be characterized by psi rit, where ri represents the position coordinates relevant to the system of the study. Now, let psi k rit, it denotes the kth member probably in the ensemble. Okay, in the ensemble you have eta number of systems, and this is the function corresponding to the kth system of the ensemble. Okay, suppose the kth system in the ensemble, suppose it is in the state base at time t. Okay, now the time variation of the wave function, these are all known to you, is determined by the Schrodinger equation, right? So H cap psi k is this. Now introducing a complete set of orthonormal functions, the systems. When you talk about the state of a system, then you write the wave function in terms of basis vectors which are complete, right? Because it can define a complete vector space, right? That's all are known to you. And therefore, I can always expand, I can always write this wave function in terms of a complete orthonormal basis functions. Those are, say, denoted by phi n. Then I write psi, this is the wave function corresponding to the kth system of the ensemble, and that is, of course, sum over n raised to 1 to infinity, a n k t and phi n, where this coefficients a n k, you know how to write it. This is the projection, right, of this wave function on this phi n. You see. আচ্ছা মনীষা, হ্যালো মনীষা, মনীষা,
হ্যাঁ স্যার।
কি হয়েছিল তোমার এত দেরি হলো?
স্যার ওই ক্লাস হচ্ছিল, এখনই ছাড়লো একটু আগে।
কার ক্লাস গো? কার ক্লাস?
স্বপনদার।
কিন্তু স্বপনদার ক্লাসের অনেকেই তো জয়েন করে গেছে।
হ্যাঁ স্যার ইয়ে করতে গেছিলাম, ওয়াশরুম গেছিলাম, দেরি হয়ে গেছিল।
2 ঘন্টার ক্লাস নাকি ওইটা আগেটা?
হ্যাঁ 2 ঘন্টা ক্লাস।
So A and K, this one is, from quantum mechanics, how to get the projection of this state on this phi n, right? So that's how you get the coefficient. This coefficient is phi n star psi k t d tau, on physical volume. So integrate over limits. So this phi and d tau is small element of volume in the real space, as I said, and then you recall the Schrodinger equation. Time dependent Schrodinger equation is this. Okay. Then you just substitute the expression for psi k, and this would be sum over this, and this side is h cap, and this is psi. And then if you take the d dt, of course this is the time dependent, and this is not time dependent, phi n, you know very well, and therefore you can write a n dot. This means d dt, and this side is as it is. Now next step is you multiply by phi m star on both sides, and then integrate over d tau, okay, on both sides. Then what you get is, this is the sum over n, and this is the integration over tau. So this is the integration over this phi and phi star, right? So you separate the integration, and then take the sum over this, and this side also you see this phi m star h cap and phi n, and the other stuff will remain the same, that is independent of the integration, and therefore take the sum outside, and then you keep it this integration and this. And next step is basically since this is orthonormal set, and therefore this will be delta mn, and this side, this is the kind of matrix element. You just remember the notation, the way notation is written, the index is written. This is m phi m star h cap phi n, which is written as h m n. When you are writing m means phi m star, okay? So basically this is phi m, and this is bra phi m h ket phi n, okay? So that notation you must remember when you are using this notation. And then this side is this, and therefore if you remove what is that? What happened? Oh, okay. You sum over this, then delta mn is there, so n is replaced by m. So am dot k is basically sum over n h m n and a n k t. Okay. So this is the equation in terms of the coefficients you get. We store this equation in as equation number 4. And index m and n are interchange. আমি করেছি আমার মতো করে করেছি, দিয়ে লাস্টে আমি এটাকে ইন্টারচেঞ্জ করছি m and n। আমার যেটা বেরিয়েছে, আমি m টাকে n বলছি আর n টাকে m বলছি, করে আমি এই ইকুয়েশনটা লিখছি, হ্যাঁ, where h nm equals to phi n star h phi m d tau। আমি এটা করলাম কেন? This is I did only to be in line with the Patria's notation. Okay, since I am totally following Patria, and that's why this I did, I didn't bother about the notation, so I did it, and eventually I tried to match with the Patria's notation. Okay, so this is that, and that's why I interchange m and n. Okay, so the physical significance of the coefficients, আচ্ছা এইগুলো তোমরা নিজেরা অলরেডি পড়েছো না অভিষেক? অভিষেক?
হ্যাঁ স্যার।
হ্যাঁ, তো তুমি কি তোমার মানে নোট বানিয়ে নিয়েছো অলরেডি?
না স্যার এখনো হয়নি।
আচ্ছা, চলছে?
হ্যাঁ।
So the Suman, probably you did it, probably, right? হ্যাঁ সুমন, তুমি কি অলরেডি এগুলো করে ফেলেছো? করতে শুরু করো, বুঝলে তো? কারণ ওটা তোমাদের প্রজেক্ট হিসাবে আছে, তো আমি ভেবেছিলাম তোমাদের প্রজেক্ট আছে, তোমাদের আরো সুবিধা হবে আর কি, কিছুটা নিজেরা অলরেডি পড়েছো, হ্যাঁ, কোথাও বুঝতে পারোনি হয়তো সেগুলো ক্লিয়ার হয়ে যাবে। এনিওয়ে, so try start reading that, and prepare your project. The physical significance of the coefficients, you all know what it is. So in this equation, you know that they are the probability amplitudes, right? For the now you see, so the physical significance of this, actually physical significance of this means this mod square. It has that would correspond to the probability, right? That you all know. Then what is the significance of, let's say, n k t mod square? What is the significance? The probability amplitude of kth system of the ensemble to be in the respective states phi n, to be keep practical, the number to be practical. That is, whatever I explained, to be practical, the number, this represents the probability. Probability of what? Probability that a measurement at any time t, it finds the kth system of the ensemble to be in the particular state phi n. Okay, so this mod square, it tells you that the probability of finding the kth system to be in the state phi n. So that is the physical interpretation of this. Now, if you sum over n, that means what is the probability that the kth system should be in any of the states? Okay, then that of course should be 1, right? So do you all agree with this? This sum over n, a n k mod square equals to 1. Do you agree? Yes or no?
Yes, sir.
Okay. So then I keep it aside and I will probably use it later. Okay. Now we introduce. So basically what we have said here, we have said how the coefficient, we write down the wave function of a system in ensembles, the kth system. We write the wave function in terms of basis vectors, orthonormal set of basis vectors. Okay, and then that depends, of course, in under which potential the system is, right? Depending on that, you will have that complete set, okay, of orthonormal set of wave functions. Now, any arbitrary wave function for a system, the kth system of the ensemble, that can be written as a superposition of those complete set of basis functions phi n. Okay, and then you look at how the probability evolves. That means how the coefficient a n k t evolves with time, and that is represented by this equation or this equation. And again, what is the physical interpretation of this a n k mod t square? This is the probability, of course. This probability is the probability of that the kth system of the ensemble could be found in the state n. Okay, then what is the probability that the kth system could be found in any of these states? It has to be 1, because anyway the system has to be in any of these states, all possible states. Okay, sum over all possible states, that is 1, and that is what we have kept around. Now we introduce the density operator, rho cap. We introduce a density operator which is denoted by rho cap, as defined by the matrix element like this. So what is this? This is rho mn is the matrix element of this operator. Okay, this is an operator, and you know from quantum mechanics, an operator can be written in the matrix form, right? So the matrix, this element, matrix element mn, is defined like this: that 1 by eta means, and then sum over eta, sum over k equals to 1 to eta, and on what? This is amk an star. Again, remember how I am denoting the index. This is mn. It was different from hmn, right? Mn is amk or ank star. Okay, that is mn in this case, rho mn. Okay, I'm defining it like this, and then you see I'm taking sum over all the systems. Okay, so all the systems. It is simply, what does this mean actually? AMK, ANK star. What does this mean? It probably means that some particle is created at N and destroyed at M. That means kind of a transition from mth state to nth state, something like that. Okay, so you can visualize in that way. Okay, it is a kind of transition from one state to another. Okay, so and that is represented by this matrix element. And when you are summing over all systems and then taking 1/8 the number of systems, that is the ensemble average. Okay, this is the quantity ensemble average, right, of this quantity. Now you are taking this quantity, then summing over all the systems and divided by number of systems. In the ensemble, you have so many systems, and this is the kind of ensemble average. So it is clear that the matrix element Mn rho Mn is the ensemble average of the quantity which varies member to member in the ensemble. This particular element that could be varying, right? That is what the beauty in quantum mechanics. Classical mechanics probably it will be the same, but in quantum mechanics it could differ as you go from one system to another, right? Now, in particular, the diagonal element rho MNT is ensemble average of the probability ANT mod square. Diagonal element means it should be NN, right? It should not be NM. That is my mistake. In particular, the diagonal element rho NNT is ensemble average of the probability ANT mod square. The latter itself being a quantum mechanical average. Quantum mechanical average that you will see, of course. Thus, we are concerned here with the double averaging process. Once, due to the probabilistic aspect of the wave function, and again due to the statistical aspect of the ensemble. Okay, once you want to get this ANT, then you take one averaging process, and then you take the ensemble average. Okay, there are two kinds of averaging processes. Two kinds of averaging two kinds of averaging processes that you have here. So the quantity, now the quantity rho in n represent the probability that a system chosen at random, okay, from the ensemble at time t is found to be in the state phi n. Okay. Now, if you again sum over, so this you understand, right? That the quantity rho n and t is represents the probability that a system chosen at random from the ensemble at any time t is found to be in the state phi n. Okay, because you take the average, right? Now you sum over n, then you see if you definitely it has to be again one. You see, if you take sum over this, then this is like this. Then 1/8 you take out. Then sum over k equals to 1 to n. Then bring this n here, and this is 1. Then 1/8 you sum eta times. Then 1/8 times eta is 1. Okay. This is also 1. Sum over rho nn equals to 1. Okay. So on the average, the average value. On the average, and this is the probability that on the average, a system could be found in the state phi n. And then you sum over all, then you get 1. And that is also quite physical. Now we shall now determine the equation of motion for the density matrix. Okay, rho m and t. We obtain with the help of the foregoing equations. Okay, we will leave these languages. Okay, so basically you look at this I h cut rho mn dot. Okay, rho mn t is known to you, right? You have the expression earlier. What is rho mn t? It is there. This one is this. So you are taking the derivative, right, with respect to time. Then if you do it, you will have one dot on this and another dot on this. These are two terms, and then just look at these expressions and see if it is quite justifiable or not. If you don't, if you feel that it is not justifiable, then please raise your question. Okay. Now again, you know that the governing time varying governing equation for the coefficients we already derived in the very beginning. So we borrow those expressions and put it here, right? In dot this case and in dot for this dot case. Okay. So you, if you recall, the very first this is the equation we have, right? Equation 4. You can use this equation, equation 4. What is that? Yeah. So you can use the equation 4 and you can write like this, right? HML ALK sum over L. Similarly here, NL star and then ALK star and sum over L. Now you see, 1 by eta you have taken it inside, sum over L you have taken out, and then HML, because sum over L is fine, you can put it here, and then 1 by eta has been taken inside, then 1 equals to 1 to eta, and ALK star. Okay, and this one is known to you. This is rho LN, right? Rho LN. Now let's say this side. This side, HNL star equals to, I have written it as HNL. That is because these are Hermitian operators. Okay, we are assuming those are Hermitian operators. Okay? So you can write it as HNL star. It can be written as HLN. And then similarly, you have taken this L summation out, and this eta you have taken inside, and the K summation has been taken inside, and therefore this is again rho ML, right? Rho ML. So you write, keeping the index, sequence. So you write this rho ML HLN. Okay. Now this, of course, this is what rho M and dot. Okay. So that is this MLLN. MLLN. So Mn. So this is the quantity. If you sum over L, then certainly it is the matrix element Mn. So IH cut rho Mn dot is basically H rho cap minus rho H cap Mn. So IH cut rho cap dot equals to the commutator H rho cap. This is, we stored this in equation 9. Okay, so this equation 9 is the quantum mechanical analog of the classical equation of Lagrange, right? So we have seen this kind of equation earlier, right? Now, if the given system is known to be in a state of equilibrium, the corresponding ensemble must naturally be stationary, right? We already talked a lot about stationary state, steady state, and equilibrium state, right? Hence, rho Mn dot should be 0, right? Rho Mn dot should be 0. I mean, there will be, what does this physically mean? That means physically means, in such situation, that you will see, we'll talk about it. In such situation, the density operator rho cap must be an explicit function of the Hamiltonian operator H cap, and the Hamiltonian must not depend explicitly on time. Okay, so rho cap should be, because this commutator has to be 0, and therefore rho cap should be a function of H cap. Okay? And if H is explicit function of time, rho will also have the explicit form time dependence. Okay, then del rho del t will come in the picture. Okay, and that is what we say, that both rho has to be rho function of H cap and H cap dot should be 0. Okay, to have this to be value rho dot equals to 0. Okay, we have this rho dot 0. Now, if the basic function phi n were the eigenfunctions of the Hamiltonian itself, then the matrix H and rho would be diagonal, right? So if the basic functions, you read this, if the basic functions phi n were the eigenfunctions of the Hamiltonian itself, then the matrix H and rho would be diagonal. right? Because if they commute with each other, then definitely they will have the simultaneous eigenfunctions, right? If those are the eigenfunctions of the H, they are also eigenfunctions of the rho, and therefore both would be diagonal, and therefore we can write rho mn equals to rho n delta mn. When m equals to n, then only we have the coefficient in the diagonal, otherwise it is 0. The diagonal element rho n being a measure of the probability that a system chosen at random from the ensemble is found to be in the eigenstate phi n will naturally depend upon the corresponding eigenvalue En of the Hamiltonian. Now, the precise nature of the dependence is, however, determined by the kind of ensemble we wish to construct. In any other representation, so this is one representation, that is the diagonal representation we say generally, right? If under that set of functions, if the operators are diagonalized, if the only diagonal elements exist and others are 0, then we say that is the basis under which the system is diagonalized. There could be any other representation also. In any other representation, the density matrix may or may not be diagonalized. However, the quite generally it will be symmetric. Rho mn should be equals to rho nm. Okay. Now, the physical reason behind such symmetry, okay, rho mn equals to rho nm. What is the meaning of this physical? What is the physical meaning of this? This physical meaning is that the statistical equilibrium, the tendency of the physical system to switch from one state to another is compensated by the similar tendency in the reverse direction. From M to N state, the tendency to go over from M to N will be compensated by the back tendency to be from N to M. Okay, so that's how that is why in statistical equilibrium the matrix will be symmetric. Okay, it may not be diagonal if you do not have a diagonal representation, and in other representation it must be symmetric. This is the kind of operator representation that I have shown here. How you rho KL, how do you get now let us consider the expectation value of a physical quantity G. Okay, now basically what you are interested in generally in quantum mechanics and other things, what you do, you try to look at the expectation value of the operators, right? And that is what is the measurable quantity, right? So the physical quantity G, which is dynamically represented by an operator say G cap, this will give the double averaging, one the quantum mechanical average and the other is statistical or ensemble average. Okay, let us look at it. আচ্ছা, কোনো প্রশ্ন আছে এখান পর্যন্ত? Okay, so so the average G is 1 by eta. Now ensemble average given 1 to 1, and then this is the average quantum mechanical average. So I was talking about the double averaging. That double averaging is this, that one is the quantum mechanical average over the wave function, and another is the ensemble, is statistical average. Okay, so this is this, and then psi again you represent in terms of the basis set, this and this, and therefore if you just look at those steps, okay, carefully, at case to 1 to eta, then sum over mn a n k star a m k, then integration phi m. So basically this integration is over only these wave functions phi n star g cap phi n d. Okay, and that is equals to 1 by eta case to 1 to eta sum over mn a n k star a m k, and this is g n m, n star m, so g n m. That is how we wrote the Hamiltonian matrix also. Now what is GNM? You are averaging over, summing over K, and therefore you can take this out, right? So you can keep the sum here, NM, and then you can carry out this sum 1 by eta this, and this one is known to you. This is your rho mn, right? Then this gives you sum over. Just hold on a minute. One all. Hello. So yeah, sorry for the interruption. Um, yeah. So you have um, basically. Yeah. So this is the expression that rho m n and g n m n. So you see the matrix elements, and then sum over n and m, right? That means this is rho m m rho g this m m rho g m m, and then you are summing over n, and that is what, of course, if this is the matrix element, and then sum over all m and the diagonal elements, then that would be nothing but the trace of rho cap g cap. Okay, so this expression you see, once you just look over that, g average is basically trace of this. But one thing it has to be remembered, that when g cap is identity, then identity average is basically trace of this equals to trace of rho. Okay, and that is, of course, has to be 1, right? So, so basically, if you want to write G average, in wave function, if you just compare this stuff with the average you have done, worked out in quantum mechanics, never forget to normalize it. Whenever you have a net gate question, wherever you are asked to do the average, get the average, never forget to take the normalization factor. Okay, psi, uh, you know. The brass psi, ket psi in the denominator. Okay, same thing you do it here also to get the normalized average. Okay, trace of rho cap g cap, and then here it is trace of just rho cap. Okay, this is related to the probability density, right? So this is the fundamental expression in this under the operator representation, that average of a physical quantity is trace of the operator product of rho cap g cap by trace of this operator rho cap g cap by trace of the rho cap. Rho cap is the your probability density matrix operator. Now, the average quantity must be independent of the choice of basis, right? And that I hope that you understand that average, that would be independent of the choice of the basis set, right? It can be a diagonal set of basis, it can be other set of basis. However, the average should be invariant, right? Now, statistics of various ensembles. Okay, you have three kinds of ensembles, that is microcanonical, canonical, and so on. Now let us look at the microcanonical ensemble. In microcanonical ensemble, the systems constituting the ensembles are characterized by NVE delta, where E minus half delta less than equals to E less than equals to E plus half delta. We have already seen this earlier. Now the total number of distinct microstats that we denoted by this gamma, NVE and delta, and we have an assumption that any of the microstats are equally probable, right? That we have already seen. Thus, the density matrix rho mn, which is diagonal in energy representation, will have the form delta mn equals to rho n delta mn if it is in the energy representation, I mean diagonal representation. Then certainly rho n should be 1 by tau, because all states are equally probable, and otherwise it will be 0 for all other states. These are the accessible states, these are the possible probable states. Okay, then if the probability density, that probability, that should be 1 by tau. Okay, in the case of tau, when tau is 1, this pure state, then every system is in the ensemble has to be in the same state, because there is only one state, right? Then the system, all the states, all the systems in the ensemble, they have to be in the identical state. Thus only one diagonal element is unity while all others are 0. Then rho square has to be equals to rho, right, in the energy representation. In the other representation, let us see what happens. In other representations, then it may not be diagonal, and therefore rho mn equals to 1 by eta, sum over this you know, and then if you sum over this, then you say this is you remove the k index and say an star, because all systems are in the same state, right? It is also, of course, I mean it is also true that pure state means all systems are in the same in a similar kind of states. Okay, and here it is only one state, but if you take this is a pure state, means it is only in the one state, and of course it is it is represented the diagonal representation. But if you go to another representation, then it may have other elements non-zero, right? So but pure state. Okay, all systems are in the same kind of state. Okay, then you see you can write rho mn square is sum over L rho ml rho ln, and then that should be am al star al an star. And if you bring this sum an appropriate place like this, am sum over this an, and you know this is 1, and therefore am n star rho mn, then it holds true for all representations, right? So rho square is rho. So again, we repeat that in any other representation for a pure state, it should be rho square equals to rho. That holds for all representations. In the case when tau is greater than 1, that is a mixed state. Okay, mixed state, then the density matrix in the representation is given by, of course, rho n equals to 1 by tau allowed states and is 0 for all other states. To ensure that all off diagonal elements are 0 and the diagonal elements are equal to each other holds for any representation, we invoke another postulate which is referred to as the postulate of random a priori phases. So we introduce some phases, okay? Even though the probabilities are same, but they could be different in the phase, and that's why we introduce some phase. And this is yet another postulate that you introduce some phase with these amplitudes, okay? And that is called the uh, um, uh, postulate of random a priori phases for the possibility for the probability amplitudes an, which is in turn implies that phi k for all k is an incoherent superposition of the basis. Okay, incoherency you get you tag some phase with this. Okay, so this will not be of great use though, this microcanonical. Canonical, of course, it will be of use in this ensemble, in the canonical case. This is mostly very important, and of course, in case of phase transition sagas, this grand canonical plays a very important role. Okay, as we have already explained, or touched upon the fact when we are talking about grand canonical ensemble in the classical approach. Now, in this ensemble, the macro state of a member system that we already know in terms of N, V, and T, the energy E now becomes a variable quantity. The probability that a system chosen at random from the ensemble possesses the energy ER that is determined by the Boltzmann factor E to the minus beta ER that we already know. Now, the density matrix in energy representation is therefore taken as rho mn equals to rho n delta mn, right? And therefore, this rho n is nothing but, this is the kind of factor. So in this case, this rho n, as in this case, it was 1 by tau, since all states are equally probable, but the here probability goes as this factor, and therefore rho n is taken as c e to the power minus beta en, and n runs from 0, 1, 2, and so on. Now, rho n is c e to the power minus beta en, and it is 0, 1, 2. Now the constant c is determined again, to normalize this, and therefore it is again, we have seen this earlier, right? The similar stuff. This is 1 by this, and therefore rho n is e to the minus beta en by q n beta. It is the canonical partition function. Okay. Now rho cap, the operator representation is like this. This is operator, right? Psi of n rho n phi n, and with sum over phi n. If rho n is not there, it is identity operator, right? But rho cap operator is like this. Okay. So this can be written as this phi n, and then this rho n is this e to the minus beta en by q n beta, and then this get this is get, and this is a phi n. Okay. And then if you write in the operator representation, the operator form, then of course you can write it in 1 by q n beta e to the minus beta h cap, and then this, or you can write e to the minus beta h cap by q n beta. Okay. Or in the matrix representation, certainly the way you write the matrix is basically, and this is, this is 1, right? This is the identity. So in the matrix representation, you write e to the minus beta h cap is basically phi 1, this, phi 1, phi 1, this, phi 2, phi 1, this, phi 3, and so on. This way you write the matrix, and this matrix representation, in the matrix representation, of course, you can see if it is in the, if these are the eigenfunctions of the H, then you will have a diagonal elements, and those elements will be minus beta 1 rest will be 0, and these are the things will be this, and therefore trace of e to the beta h cap is sum over n e to the minus beta n, which is nothing but q and beta, and that is why, and hence e to the power rho cap equals to e to the minus beta h cap by trace of e to the minus beta h cap. Okay, this is your rho cap. Look at this once. Okay. দেখছো?
ইয়েস স্যার।
একটু দেখে নাও, দেখে বললো স্ক্রল ডাউন করবো এবং নিজের চোখে দেখে নাও জিনিসটা।
ইয়েস স্যার, স্ক্রল ডাউন করতে পারেন।
হুম 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 হুম।
আমার দেখা হয়েছে, ওর বাকিটা জানি না, এতদূর দেখা হবে।
বাকিরা বলো। সমশ্রী, শ্রেয়সী, গোবিন্দ, বিপ্লব,
হ্যাঁ স্যার দেখেছি।
ঠিক আছে?
হ্যাঁ
আর নিচেটা স্ক্রল ডাউন করবো? হ্যাঁ বলো, তুলবো?
ঠিক আছে।
So, so this is vocab, right? That we have seen. Now, আমরা এটা অলরেডি দেখিয়েছি যে G average is basically this আমরা কি দেখিয়েছি? G average trace of কি দেখিয়েছি ওখানে? কি দেখিয়েছিলাম? G average টা কোথায়? G average, yeah. So trace of rho cap G cap by trace of rho cap, তাই তো? তাহলে এখানে কি হচ্ছে? এখানে হচ্ছে ঠিক, দেখো তো একটু ক্যালকুলেশন করে। এটা কেন আমরা এই যে ওখানে করেছিলাম কি ট্রেস অফ রো ক্যাপ জি ক্যাপ বাই ট্রেস অফ রো ক্যাপ, তাই তো? এখানে ওটা ট্রেস অফ রো ক্যাপটা নিচে করলাম না কেন? That is because
1 বলে।
we have already normalized it, right? This rho cap is already normalized, right? And that is it. You are right. Yeah, exactly. Then you come to a grand canonical ensemble. Okay? তোমাদের কোনো ক্লাস নেই তো আজকে?
না, নেই।
আজকে কি প্রচুর ক্লাস করেছো তোমরা?
মানে কন্টিনিউয়াসই হয়েছে আজকে।
আচ্ছা 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 আচ্ছা। ঠিক আছে, ঠিক আছে। আমি এই গ্র্যান্ড ক্যানোনিক্যাল এনসাম্বল এটা আমি না হয় কালকেই বলবো। কালকে আমার সকালে কখন ক্লাস আছে গো তোমাদের? সকালবেলা না?
9:30 থেকে 11:30।
9:30 থেকে 11:30। ঠিক আছে, তাহলে কালকে একটু এনার্জি নিয়ে থেকো, কালকে এটা বলবো। আর বোধহয় আর একটা সপ্তাহ পাওয়া যাবে আমার মনে হচ্ছে। হ্যাঁ, আর একটা সপ্তাহে আমি বুঝতে পারছি না কি করা যাবে। এটা তো কালকে হয়ে যাবে, হয়ে আরেকটু হয়তো মানে দেখা যাক কি করা যায়।
আর স্যার পিডিএফটা, মানে পিডিএফটা দেওয়া হয়নি এটা।
দিয়ে দিচ্ছি, আমি দিয়ে দিচ্ছি, পাঠিয়ে দিচ্ছি। হ্যাঁ, ঠিক আছে।
ওকে স্যার।
Extremely sorry sir, won't be repeating. বিপ্লব, বিপ্লব তুমি কখন ঢুকেছো আমি দেখিনি, খেয়াল করিনি। এনিওয়ে বিপ্লব তুমি তাহলে এটা পাঠিয়ে দিও অ্যাটেন্ডেন্সটা।